There's a metal that can handle extreme heat, resists rust like a champ, and is strong enough to be used in fighter jets, but light enough to float in seawater. It's not steel. It's not aluminum. It's something way cooler. Titanium. You see it in luxury watches, high-performance bikes, dental implants, and even spacecraft. But what's strange is, you almost never see where it comes from or how it's made. And that's because the process, it's intense. We're talking fire, gas, salt, and one of the most complicated extraction methods in the entire metal industry. It all starts with a chalky white rock that looks like something you'd ignore on a hiking trail. But inside that rock is one of the most valuable metals on Earth. The path from that raw mineral to the shiny, corrosion-resistant titanium we know involves crushing, chemical reactions, and high-temperature furnaces that run hotter than a volcano. And here's the wild part. Despite how advanced it is, the way we make titanium hasn't changed much in nearly 8 years. There's still one process at the center of it all, and it's so dangerous and energy-hungry that titanium costs up to 10 times more than steel to produce. So, why do we go through all that trouble? Why do we burn through tons of energy just to get a few kilograms of this metal? And how does something that comes out of a dirty ore end up inside a jet engine or orbiting the Earth? In the next few minutes, we're going deep into one of the most dramatic transformations in the world of materials, the making of titanium. What you're about to see is gritty, risky, and full of science that's borderline magic. The rock that looks like nothing, but holds everything. At first glance, titanium doesn't look special at all. You won't find it shining in the ground or sitting around like gold. In fact, it hides inside two very boring-looking minerals, ilmenite and rutile. They look like plain gray or black rocks you might step over on a trail without even noticing. But inside them lies something powerful. These rocks are full of titanium dioxide, a white powder that's the main ingredient for making titanium metal. And here's something crazy. Titanium is the 9th most common element on Earth. It's in the soil, in plants, and even in your body. But turning it into usable metal? That's the hard part. Ilmenite and rutile are found in places like beach sands, riverbeds, and old volcanic areas. Countries like Australia, South Africa, and India have huge deposits. These minerals are mined using big machines that scoop them up by the ton. The rocks don't sparkle. They don't stand out. But they hold something stronger than steel, lighter than most metals, and resistant to rust. What's really interesting is how this nothing-looking rock has become a key part of spacecraft, airplanes, and medical tools. A rock you'd never notice is helping people fly faster, heal better, and build stronger machines. So next time you walk past a dull, dark stone on the ground, think about this. It might just be hiding one of the most high-tech materials we use today. That's the mystery of titanium. It hides in plain sight, waiting to be unlocked. Mining the hidden metal, titanium, might be hiding in plain rocks, but getting it out of the ground is no easy job. It doesn't sit in chunks like gold or copper. Instead, it's spread out inside minerals like ilmenite and rutile, mixed in with sand, clay, and other materials. That means mining titanium is all about finding the right spots, and then collecting a huge amount of material just to get a little titanium. The most common places where titanium-rich minerals are found: beach sands, ancient riverbeds, and old volcanic regions. These are called placer deposits. In some places, the sand itself is loaded with titanium minerals. It sounds strange, but it's true. Black sand beaches in countries like Australia, India, and Mozambique are actually full of ilmenite. Miners use massive equipment, bulldozers, excavators, and dredgers, to scoop up tons of sand and soil. The mix is then taken to nearby plants where the real work begins. But here's the wild part. Only a small percentage of the sand they collect contains titanium. The rest is waste. So just to get 1 ton of usable titanium ore, they may have to move hundreds of tons of earth. This process has to be done carefully. If not, it can hurt the local environment. That's why modern titanium mining uses rules to protect wildlife, water, and land. Some companies even restore the land after they're done, planting trees and cleaning up. What's amazing is that something so advanced, used in jet engines and spacecraft, starts its journey in something as ordinary as beach sand. The next time you see black sand slipping through your fingers, you could be holding the first step in the making of titanium. The art of separation, crushing, and concentrating. Once the titanium-rich sand or rock is mined, it's still not ready to become metal. Far from it. What comes out of the ground is a mix of everything: dirt, clay, iron, and tiny pieces of useful minerals like ilmenite or rutile. The challenge now? Separate the valuable stuff from the junk, and it's a process that's both smart and a little bit like magic. The first step is crushing. Big chunks of rock are broken down into smaller pieces, like gravel. Then it's crushed again into a fine powder, almost like sand. This makes it easier to pull out the titanium-rich parts. Next comes concentration. Here's where the science kicks in. Titanium minerals have different weights and magnetic properties compared to the rest. So machines use gravity, magnets, and water to sort them. One method uses a spiral separator, a tall, twisting slide that spins the mixture so heavier minerals move one way and lighter waste flows another. Another trick is magnetic separation. Ilmenite has iron in it, so it reacts to magnets. Powerful magnetic belts pull it out while the rest is left behind. By the end of this stage, what you have is called a concentrate, a dark, heavy material packed with titanium minerals. Still not metal yet, but now it's in a form that can go to the next phase, chemical processing. Think about it. This is the moment where useless dirt is turned into a source of something valuable. It's not loud or explosive, but it's clever. The perfect mix of brain and machine, quietly preparing titanium for its next transformation. From mineral to metal, the magic of the chloride process. Now that we've got a titanium-rich concentrate, the next step is where things start to feel more like science fiction than mining. This is where the chloride process begins, an intense, high-temperature chemical reaction that transforms black mineral powder into a toxic, invisible vapor. Sounds crazy, right? But this is the only way to get closer to pure titanium. The concentrate, usually full of ilmenite or rutile, is first heated to very high temperatures in a sealed reactor. Then, chlorine gas is pumped in. At these extreme conditions, the titanium in the ore reacts with chlorine to form a clear, colorless liquid called titanium tetrachloride, or Tichl-4. Here's the wild part. Tichl-4 looks like water, but the moment it touches air, it turns into a thick, white smoke. It's toxic, it's dangerous, and it has to be handled with extreme care. Workers wear full protective suits, and everything happens in controlled environments. But this liquid is pure titanium in chemical form, and that makes it gold, well, metaphorically. During the process, unwanted elements like iron, magnesium, and silica don't react the same way. They're filtered out, leaving behind only the valuable Tichl-4. This liquid is stored in sealed tanks, away from air and moisture, waiting for the final step where it'll become solid titanium metal. It's strange to think that a solid rock was just turned into a ghost-like liquid that can burn your skin, and yet, it's a key step in making one of the toughest metals in the world. Titanium's fiery birth, the Kroll process. This is the moment titanium is truly born. After all the crushing, separating, and chemical reactions, we now have a clear liquid called titanium tetrachloride, or Tichl-4. But it's still not metal. To turn it into real, solid titanium, we need one more process, and it's one of the most dramatic steps in all of metal production, the Kroll process. Invented in the 1940s by a chemist named William Kroll, this method is still used today. Why? Because no one has found a better way. It works, but it's not easy. Tichl-4 is poured into a large, sealed container called a reactor. Inside, it's a special metal called magnesium. Now here's where the fire comes in. The whole thing is heated to over 1,000 degrees Celsius, 1,832 degrees Fahrenheit. That's hotter than lava. At that temperature, the magnesium pulls the chlorine atoms away from the titanium tetrachloride. What's left behind is pure titanium. But it doesn't look like shiny metal just yet. It forms as a gray, spongy mass called titanium sponge, light, porous, and full of trapped gas. It takes days to complete this reaction, and once it's done, there's still magnesium and leftover chloride stuck in the sponge. That means another step: washing, breaking, and cleaning the sponge to get rid of anything that's not titanium. It's a fiery chemical ballet that turns a ghost-like vapor into solid metal. It's dangerous, expensive, and slow, but it works. This is the true birth of titanium, the moment it stops being chemistry and becomes one of the strongest, most valuable metals on Earth. The sponge that weighs like a feather. Once the titanium has gone through the Kroll process, it's time to meet the most unusual part of the metal-making journey: titanium sponge. At this stage, titanium still doesn't look anything like the shiny metal we're used to seeing. It's actually a rough, spongy, porous material that looks like something you might find in a science lab, not a jet engine. Here's why. The Kroll process doesn't turn titanium directly into a solid, dense piece of metal. Instead, it creates this light, airy material with a texture similar to a sponge you'd use for cleaning. Imagine a chunk of metal that weighs almost nothing for its size. This is titanium sponge. It's fragile and full of holes, like a block of metal that couldn't decide if it wanted to be solid or gas. What's fascinating is that despite its spongy appearance, it's still pure titanium, just in a form that's not ready to be used yet. At this point, it's soft, flaky, and brittle. It's nothing like the titanium we see in high-performance gear, bikes, or spacecraft. But this sponge is important. It's the raw material that will later be processed and shaped into usable titanium metal. The next steps will compress and purify it into solid pieces that can be forged, molded, or cast into whatever shape is needed. So, even though titanium sponge might look weak and strange, it's one of the most important parts of the process. It's like the raw clay before it gets turned into a masterpiece, and from this sponge, melting the unmeltable, turning sponge into ingots. Now the titanium sponge has reached its next big challenge, turning it into something useful. But here's the thing, titanium is notoriously hard to melt, but in its sponge form, it's still far from the metal we use in planes and rockets. The journey from sponge to usable metal involves some extreme heat and some serious technology. To melt titanium sponge, you can't just throw it in any furnace. It needs to be melted in a vacuum arc furnace, VAF, or electron beam furnace. These are specialized furnaces that can reach extremely high temperatures, about 1,650 degrees Celsius, 3,002 degrees Fahrenheit. That's hot enough to melt the titanium sponge without it reacting with oxygen, which could ruin the metal. Inside the furnace, the titanium sponge is placed in a vacuum, a sealed environment with no air. Why? Because titanium reacts with oxygen, nitrogen, and even hydrogen. If exposed to air during the melting process, it could end up with dangerous impurities, making the titanium weak and brittle. So, creating a vacuum helps ensure the metal stays pure. Ingots are the basic shape from which all titanium products are made. Whether it's an aircraft part, a medical implant, or a titanium watch, it all starts with an ingot. This melting process is a bit like creating a perfect alloy. It's an art that turns rough, fragile sponge into the strong, solid material we rely on for so many high-tech applications. Shaping the future, forging, rolling, and machining. Once titanium is turned into solid ingots, the real magic happens, shaping it into the final forms we can use in everything from aircraft engines to surgical implants. The first step in shaping titanium is forging. Forging is when you take a solid piece of metal and press or hammer it into shape while it's hot. Think of it like molding clay, but at extremely high temperatures. The goal is to make the titanium more flexible, so it can be stretched or shaped without breaking. It's like giving the titanium extra strength before it's shaped into the final product. Next comes rolling. This is when titanium ingots are pressed through rollers to form long sheets, thin plates, or strips. These sheets of titanium are what you'll see in everything from aircraft wings to high-performance bicycles. Rolling makes titanium thinner and more uniform, which is important for creating parts with precise dimensions. After rolling, it's time for machining. This is where the fun happens. With tools like lathes, milling machines, and CNC machines, the titanium is cut into exact shapes. This could mean cutting out tiny parts for a watch, or shaping huge pieces for a jet engine. Machining is a high-precision job, and it's crucial for making sure every part fits and functions perfectly. All these steps turn titanium from a tough, rough material into sleek, precise components. And while it's a complicated process, it's what makes titanium one of the most versatile and reliable materials in the world. Why it's so expensive and worth every penny. So, after all this effort, why is titanium so expensive? Why does something that starts as a dusty rock end up costing 10 times more than steel? The answer lies in the complexity of the process and the amount of energy it takes to turn that rock into the titanium we know. The whole journey, From mining the titanium-rich minerals to crushing, chemical processing and melting is a long, difficult, and costly process. Titanium requires specialized equipment, extremely high temperatures, and a lot of energy at each stage. The Kroll process, for example, uses huge amounts of electricity to melt the titanium and magnesium, and the chloride process requires handling dangerous chemicals like chlorine gas. Another factor is time. While some metals can be extracted and processed quickly, titanium takes days of careful work. That's a lot of time and labor costs. In fact, it can take weeks to turn that raw titanium sponge into usable metal. And with titanium being so difficult to work with, each step has to be done carefully and precisely. Then there's the fact that titanium is often used in industries where safety and reliability are crucial. Aerospace, medicine, and military applications demand the highest quality materials. In these fields, failure isn't an option. The result is that titanium parts need to be flawlessly made, and that level of precision comes at a price. But here's the thing. Even though titanium costs more than other metals, it's worth every penny. It's incredibly strong for its weight, doesn't corrode, and performs well in extreme conditions. Whether it's in a fighter jet engine, medical implant, or spacecraft, titanium's ability to last and perform in harsh environments makes it an investment that pays off. The future of titanium: exploring new frontiers. Titanium has already proven itself as one of the strongest, most durable metals on Earth. But as technology keeps advancing, the future of titanium looks even more exciting. Scientists and engineers are constantly finding new ways to use titanium in ways we never thought possible before. One area where titanium is making waves is in 3D printing. While 3D printing has been around for years, the use of titanium in additive manufacturing, a fancy way of saying 3D printing, is still in its early stages, but it's already being used to create highly detailed parts for aerospace, medical implants, and even sports equipment. In 3D printing, titanium is used to build objects layer by layer. This process opens up new possibilities for creating parts that are lighter, stronger, and more complex than anything made before. Another exciting area is in biomedical technology. Titanium has been used for years in medical implants like hip replacements and dental implants, but the future looks even brighter. Engineers are now developing titanium-based alloys that can be used in bone implants that are not only strong but also biocompatible, meaning they'll be able to bond with the body without causing any issues. This could revolutionize the way we treat injuries and disabilities. Titanium is also finding its place in the world of clean energy. With its ability to resist heat and corrosion, titanium is becoming an essential material for solar panels, wind turbines, and hydrogen fuel cells. As the world shifts to renewable energy, titanium is expected to play a huge role in building the technology that powers our future. So, while titanium's journey from rock to metal might seem long, it's only just beginning. With its unique properties and ever-growing applications, titanium is set to shape the future in ways we can only imagine. Titanium may start as an unassuming rock, but it's clear that it's far from ordinary. From mining hidden minerals to transforming them into one of the world's strongest metals, every step in titanium's journey is filled with fascinating science and impressive technology. Whether it's in jet engines, medical devices, or future clean energy solutions, titanium's role in shaping the future is undeniable. Its strength, durability, and versatility make it a material worth the effort and cost. As we continue to push the boundaries of innovation, titanium will remain at the forefront. This incredible metal truly holds the future in its hands. And that's a wrap on our deep dive into the fascinating world of titanium. From the simplest of rocks to one of the most powerful materials on Earth, it's amazing how much goes into making titanium the superhero metal we rely on today. Whether it's in aerospace, medical technology, or clean energy, titanium's role in our future is truly limitless. If you enjoyed this exploration into one of the most incredible metals on the planet, be sure to hit the like button to show your support. Subscribe for more mind-blowing content like this, where we dive deep into the science, technology, and innovations that shape our world. And don't forget to drop a comment below if you have any questions or thoughts about titanium. We'd love to hear your take on how it's changing industries or any topics you want us to explore next. We always appreciate your feedback and suggestions. Thanks for watching, and remember, every material, no matter how ordinary it seems, has a story that's anything but. Stick with us, and we'll continue to explore the fascinating world around us, one incredible topic at a time.